Hello. Hi, everyone. My name is Alina. I will speak about Android malware analysis, current detection techniques, its limitations, and our proposed method to identify malware authors. So who am I? I'm doing research in Canadian Institute for Cybersecurity. I'm working mainly on Android malware analysis. Also, I'm doing security assessment of blockchain applications, smart contracts. Also, I'm working on medical IoT devices. I'm doing also PhD. I'm PhD student at UNB, and my work is concentrated mainly on software security and breaking machine learning techniques. Previously, I was doing cryptography at Swiss Federal Institute of Technology, so I have a cryptography background. But I'm more interested in applied security. I love it. So today I will start my presentation with saying that cybercrime is one of the most popularizing crimes committed today. Last year, we had more than 7 million new malware samples. And every year, we have these growing numbers of new malware samples. Android is one of the most popular mobile application platform. But with such a popularity and openness, we have a lot of hackers, malicious authors. They write mobile malware on this platform. By Kaspersky Lab, they estimated that near 98% of mobile malware is target Android devices. So current malware detection techniques, they are working by creating fingerprints or signatures of malware. So, for example, to be able to identify malware sample, we need to build a malware fingerprints database. So in this database, we have already existing Android malwares. We extracted all the features by doing static analysis and dynamic analysis, and then we can classify new application, extracting the similar feature set, and to identify is it application malicious or benign. There are a lot of different methods to be able to extract these fingerprints. For example, by doing a static analysis, we can extract features from the binary IPK file or from the source code. So we are using different reverse engineering tools to be able to extract the source code from the binary. Also, we are doing several analyses on manifest files to be able to identify what kind of permissions this Android application was used. Because some of the applications, let's say you download this note, like you want to write something, yes, you download a note application, but this application don't need, for example, to access to read phone data or read SMS, send SMS, like call phone. It doesn't need such application, so such permissions. So it seems that this application is malicious. So we extracting different features from the permissions, activities, services, receives. Also, we are doing a source code inspection by doing static analysis. So we are looking on static updates. Also, we are looking if there is dead code inside of this source code. We are concentrate on null pointer controls and termination controls. We are using different tools to be able to extract this source code from Android app. For example, we have APK file, and to be able to obtain Smiley, we are using APK tool. Then we are using DEX to jar to be able to convert DEX to jar, and from jar to Java, we are using GD GUI to use the source code. We made some analysis on this source code inspection. So we had malware sample, and we were able to see that in the source code, this malware sample actually had in clear do register user function. So it extracts a phone number and network operators by calling a get telephone company and get phone number functions. And also by looking inside of this function, we were able to identify that the IP address where it sends the data, it sends the phone numbers, network operated data, it's located somewhere in Thailand. We did IP tracing and IP tracking because we were able to see the string IP address inside of the source code of malware. But the problem is with the static analysis that a lot of malicious software which is existing now, hackers, they are smart. They are like, don't get you in clear this source code of malware, yes? This source code is mainly, it's obfuscated. They use like different kind of obfuscation, and to be able to deobfuscate such a malware sample, it's actually very hard work. So static analysis has a lot of limitation. It's sensitive to various obfuscation encryption techniques. It's don't execute the application. So we are just analyzing the source code or binary code of such application, but we are not doing don't run in this application to be able to extract, for example, features from the traffic or network activities. Also, such a features, they are time-consuming to extract such features because think about, like, we need to analyze every single source code to be able to identify, for example, if there is some malicious activities in control flow or data flow looking weird. So we need to go inside of each source code and look on it. So it's very inefficient to large-scale analysis. And also static analysis can be ineffective to metamorphic malware. For example, such a malware which is self-modifying. We, after analyzing such malware, we will not be able to look on this source code because we saw some malware that generate like new source code every 10 seconds, and you cannot be able to catch like to make the static analysis on this malware sample. That's why another approach is to add dynamic analysis on the top of static analysis. So dynamic analysis, you need to run this malware. To be able to run this malware, you need to use some sandbox or virtual machine. So, for example, for Android, it's an emulator or real device. Actually, I saw some work, like research work there, saying that to run malware on emulator, you will not be able to see all this activity which malware can create. Because malware can identify that you are running this on the emulator and hide some activities. That's why you need real phone to be able to capture the network traffic of such malware. So we have different actions to be able to monitoring actions. So we need to pay our attention on information leaks, on network traffic, API calls, also cryptography operation, because some malware, they encrypt the files, and we are looking on encryption keys or like salt of this malware. Also, we are capturing SMS and phone calls if it exists. Here it's an example, like we made analysis on the ransomware. In such a research, we wanted to actually capture the traffic of ransomware and to see if the packets, they are different from the just regular malware or benign, to be able to capture the statistics of these packets. Can we easily identify, for example, if like TCP, UDP communications of this traffic. For example, we have like more packets on TCP, UDP than any other malicious software or benign software. So we actually using Android emulator for this analysis, and we are doing with Android curler. It's distributed using fake applications such as, for example, pornographic applications. After installing this ransomware on Android emulator, we will be able to see that in real, such a ransomware encrypt all the files on your Android device. So actually, ransomware, why it's bad? Because after encryption such a files, you need to pay ransom to be able to decrypt such files. And I saw some statistics that it's saying that more than 30% of companies, they didn't receive their data back. They paid ransom, like they sent these bitcoins, but they didn't receive the data back. We saw that our pictures, for example, like we generated pictures on our emulator to be able to see if it's encrypted or not. So it's encrypted, and also you are not able to interact with the mobile device because the screen is locked. Like with the saying attention, your device has been locked up for safety reasons. After analyzing the traffic by Wireshark, we were able to see that when exactly this encryption is starting and what servers the malware is communicating. To what servers, sorry. The encryption process was started from such a IP address and from this packet, which you see, and we were able to see the key, encryption key, and salt. Here, for example, we were able to extract all the DNS servers and URLs during a ransomware communication. And we wanted actually to check every URL to be able to answer the question, is it malicious URL, and then after checking every URL, we were using VirusTotal to be able to check. VirusTotal actually very good tool to be able to check not only URLs, but also you can send APK file to be able to see if it's APK malicious or not. And they have different companies. They provide this identification of malware. Is it malware or is it benign? For example, here you can see by checking this particular URL, block Vega, three malicious. Three companies which is identify malware, they say that it's malware. Another one says it's clean. So there are also a lot of tools to be able to identify is it sample malicious or not. One of the most popular is DroidBox. So by using DroidBox, for example, you can see read operations or write operations of such a malicious sample. Also, you can see what crypto algorithms were used for doing such a encryption. There are a lot of limitations also in dynamic analysis because dynamic analysis, they request a lot of system resources. When you install this, for example, a sandbox on your device, or you installing emulator on a computer, you will need it like for every sample, and it's also time consuming to be able to capture this network traffic, because you need also to create different scenarios. For example, you need to make a phone call to see if this malware is capturing the phone number or something. So it's also very time consuming. Also, dynamic analysis as like static analysis, they are not be able to identify zero-day exploits. It's very good like for already known malware samples. We have in our databases a lot of signatures of malware, and if this new malware samples, they capture these features, yes, and we can identify this malware sample. But if we are dealing with zero-day exploits, they don't have signatures, yes, in our database. So how we can deal with this? This is a question. Also, not effective on all malware, because some of the malware, they are not allowed you to capture the traffic. Like they can easily identify if you create the fake like scenarios for this malware, and some malware, they're very tricky in this. Also, dynamic analysis, they require rooting the device. It's one of the limitations of such analysis. So, how I said before, yeah, there are a lot of antiviruses, there are a lot of firewalls, But think about if we had such a good security protection, we wouldn't have such a picture. Every single year we have more malware samples, and it's growing very fast. So what we are doing wrong? This is a question. I'm thinking about we need to concentrate who is staying behind of these malware samples and how they can be identified. Because with zero-day exploits, we are not able to identify them. We don't have this malware signature. But if you're thinking about who creates this malware, the author, because I'm pretty sure that if hacker, they cannot just create one malware for whole life, yes? It will constantly create more malware samples. Some of them, they create 1,000 or 1 million malware samples and they are selling to the market. So we need to concentrate who is staying behind this to be able to be able to protect our systems. So one of the techniques to be able to identify authorship of software is authorship attribution. It's working by analyzing the features, stylistic characteristics of code. It's not only you can use in malware forensics, for example. You can use it in plagiarism detection or ghostwriting detection or programmer de-anonymization. So it also works with benign applications too. Here just example, we have there are two types of people, yeah, but it's example only with bracket style. Some of them they use on the left side, yes, some of them on the right side of this picture. But it's only it's only one feature, okay? But with attribution we have more than 1,000. In previous research we did, we saw we identify 1 million features of the source code. Think about this. It's we cannot say, for example, we are seeing Russian comments in the source code and we are identify it's Russian. No. Maybe somebody imitate Russian people, yes, and we cannot say with 100% that no, this malware came from Russia. We need to explore everything. We need to explore servers, communication protocol, ports, encryption keys, a lot of. For example, if we are doing in source code attribution, we can capture control flow of this source code. For example, somebody uses for loops, somebody uses while loops. So we are capturing these characteristics. And this actually authorship attribution, they came from academia. It started from 1997, and there are more than 20 papers of such techniques. Some of the techniques, they receive near 97% of accuracy. And the interesting thing is that in industry, for example, I saw some video from Black Hat. They use this authorship attribution to be able to identify the malicious writer. And they use it's only in 2015. So, for example, last year in DevCon, they presented the de-anonymizing framework to be able to know who wrote the source code or binary. They presented the different features which involve this attribution. So what we are doing? In our institute, we are trying to attribute Android applications. So here we have some interesting questions to think about. In applications, we have binary code, yes? So we are not doing on source code, because you will tell me Alina, where did you see the source code of malware? Yes, there are a lot of forums where, but all malware, the source code is unavailable. And if we can identify in the source code features, after compilation, for example, bracket style, comment style, it doesn't survive the compilation. That's why we are looking on Android binary application. And we No, this year we actually wrote a paper about Android authorship attribution through string analysis. If somebody interested, you can look here. I will speak more about like our architecture, which we proposed. So we have APK file, yes? We are doing string extraction. For example, string. What we identify as string, such as URLs or encrypted data, which we are able to see in the application. We are then using machine learning approaches. So we also divide our data on the training and testing set, and we are using n-grams feature representation. Like we divide all the after decompilation, we divide all this APK on tokens, unigrams. And then we generate a feature vector from this feature n-grams, sorry. And after this, we created author profiles, like we extracted all the features which is uniquely identify the particular author, and we were able to attribute the unknown sample to the author in our dataset, author profile. So I will go through each of these steps with more details. So, for example, here we have different types of the extracted strings. We extracted reference strings. We name it referenced because these strings, they are present in DEX file, and they have linking offset linking to not only string IDs in the DEX file, but it also has linking, for example, class IDs, and in the data section too. For example, let's say we have a class name, I don't know, let's say we have attribute declaration, let's say, it's a class name. So this class name, attribute declaration, it will not only be in string IDs, it will be also in class definitions. So this is, we are calling reference string, if it has more than somewhere, if it exists somewhere, else than string IDs. Also, we have application strings. So application strings we extracted from XML resource file. For example, here you can see its example of a string XML file, and actually this is a very good example to watch, because author can write differently. Let's say Wi-Fi connection. Yes, it can use all uppercases or different. Here it uses underscore. Yes, maybe another type of sign. So this all strings which we extracted, it can identify the author style. Also, another strings we will extracted is unreferenced strings. So unreferenced strings, they are different from reference strings because they don't have reference to, let's say, class or method IDs. They only exist in string IDs. And why? Why we have these unreferenced strings? We saw a lot in malicious applications that they use code hiding technique. They hide the malicious code in the data section. And no, because they want to prevent against reverse engineering of these applications. So it doesn't, like, they don't follow Android convention to write, to write this application. So they put it anywhere they want, yes, and they don't have this linking between sections. Also, like, to be able to identify these URLs, we captured hard-coded URLs, email addresses, malicious code samples in these unreferenced strings. The fourth strings which we named it DEX strings. It's all kinds of the strings present in the DEX file, and all strings, all the type strings combined together. Why we define such a string? Because we want actually to see what kind of strings they perform better. Because some strings, like the amount of the strings are less. Let's say unreferenced string will be less than reference strings, yes? And if we can show that some particular string perform better, we can like people who will use our approach, they don't need to do this again and again. So feature generation. For example, we have two strings here, mreset and cookie value must not be null. We are using different n-gram size to be able to generate our features. 1 grams or unigrams, bigrams, 3 grams, 4 grams, and so on. Some researchers, they've already done this n-gram feature generation, and they showed, for example, for C code, if you are attributing C code, source code, the 3 grams, they perform better. But we are doing different, with different application. We are doing different strings. So that's why we need to make this analysis again and to be able to identify, particular for this Android application, what n-gram is working better. So also, we are doing a classification, APK classification. Like every machine learning approach, they need a classification. So with classification, you can use, for example, decision trees or a random forest or a neural network. But for this case, we choose SVM, supervector machine, which is, for example, it's create a hyperplane to be able to divide the data set or this, for example, on this picture on two sets, as we are dealing with two-dimensional data, but feature vector can be like 1 million of size. So we have 1 million dimension of this hyperplane. Another very interesting step is to create the dataset, because we need to check our approach, yes, on the dataset. That's why it's actually very tricky to generate the dataset. Literature review, we were not able to access the previous dataset which they used in scenario, for example, malware analysis. Why? Because they have only APK samples, but to be able to make such analysis, we need APK samples and also author of this APK sample. So we use such assumption that APKs with the same certificates came from the same developer. But we discard the APK which is signed by public certificates, because public, they can, like, everybody can use such certificates. That's why we also discarded APKs which is signed by debug certificates, and also we removed in our data set authors that has less than 20 applications. So in our data set, authors identified by the public key, by the certificates they used. So APKs was collected from different Android markets. It was collected from Google Play Store, it was collected from Applant, Angie, Aptoid, Mobile Market. Like, we actually explore a lot of different Apple Store, because we don't need we didn't want to concentrate on one, for example, Google Play Store. And the final data set which we will be able to extract, it contains 40 authors with 1,559 Android applications. And every author had more than 20 applications. Why we limited on these 20 applications? Because if somebody has, let's say, 5 applications, we cannot make a machine learning approach. Like, we cannot, it will not be enough for training to make the system work. That's why developers, they should have more than 20 applications. Another dataset which we created is a malicious application dataset. So here we had a challenge that we cannot identify authorship, or like there is no, we cannot know that this particular author, they wrote this malware sample. That's why we didn't have such a data set to check our system. But after analyzing, like go through this all forums and reading about where we can extract, find such a data set, we were able to see this Kudos. It's open source Android malware analysis platform. It has like every day, it has more than 6,000 applications, new applications. It's actually a very, very good platform. It's created for security analysts or researchers to be able to check their system, their framework, if it works or not. Every malicious sample which were generated in our data set, it was checked with virus total, because we should know exactly if it's malicious or not. So the final data set contains 10 authors with 262 malicious Android applications. And another one is obfuscated application dataset. The problem with obfuscated application, why we wanted to make it like separate dataset? Because strings, yes, if we encrypt the strings, the attribution of the strings will be lost. Like this attribution will, no, theoretically, we cannot attribute on the obfuscated strings. Yes, so the patterns will be lost. That's why we, and the problem, for example, in malicious dataset, we found a lot of people who are using obfuscation. We were not able to deobfuscate or to be able to understand what type of obfuscation they use, because it's actually a research problem to be able to identify this type of the obfuscation. It's a very hard job. That's why we make it like artificially. We created the dataset from GitHub and then obfuscate every source code or on this Android projects. So to be able to generate the data from GitHub, there are a lot of forked repositories. Like people, they contribute, yes, and we cannot identify the unique style of such a application, because a lot of people, a lot different styles, yes. We only need in our data set, we only use in our data set repos without forks. Also, we used repos which has only one contributor, because we need this uniquely coding style. Then many projects, we had the problem that many project wasn't compiled. We also discarded this these APKs. And another thing that like developers has a few Android projects. We also discarded because the same thing in machine learning, we need like have more data is better for training purposes. So the final dataset contains 9 authors with 96 source code projects. Okay, obfuscated application dataset we created by using different obfuscation tool is ProGuard, Alatori, -O. And ProGuard, for example, they used the code shrinking string obfuscation. Alatori also, they implemented string obfuscation, string encryption, control flow obfuscation, optimization. -O, they created string obfuscation, string encryption, control flow obfuscation, and optimization. Evaluation of our system we performed on 3 different kinds of the dataset. It's benign, malware, obfuscated applications. Also, we are evaluating the system over different level of IPK similarity. Why? Like we need to use this similarity? Because the problem is a lot of different APKs, they are like reusing the code. For example, authors, they are not creating it from the scratch, yeah? They are reusing. That's why, for example, if we divide in the training to testing set, yes, and we have a lot of similar like part of this APKs in the testing set, it will be unfair. If, for example, 90, or if we have the same sample on the testing set, it will be unfair to be to predict it can predict like 100% because it's already so in the training set particular sample. That's why we also evaluate the different level of APK similarity. We are using for this DroidCon, which can say how much two APKs are similar. Score. Then we are comparing the performance of different kinds of the strings, all DEX, unreferenced, and application strings. So our results, this is for benign application datasets. So we found that all strings and DEX strings, they perform the best. They perform like 98% of accuracy. But the training time, is actually pretty long. Like 606 seconds comparing with 5 seconds. For example, if we're using application strings from XML file, we will receive near 94%. Like comparing with all strings, it's like only 4% difference. But the training time will be only 5 seconds. So if somebody needs like fast, they can use application strings. We also perform analysis just from extracting the features from bytecode and opcode, but they gives very, very little accuracy, bytecode especially, 32% comparing with the all strings approach. So here there is pictures about APK similarity. And as you can see, how I told before, that theoretically, if we have more similarity between in our dataset, it will give much better accuracy. So we perform also the similarity measurements on our dataset. In malware application dataset, we received much less results comparing with the benign dataset. We received 96% and 95% on the DEX strings. And training time is less because in malware dataset we had less size. Our dataset was with less size. That's why the training time was decreased. Also, similarities threshold we seen here that if more similarity in our dataset, much better results. And obfuscated dataset results. So like we use the ProGuard, aleatory -o obfuscation on every type of the strings. And we see here as such a, for example, ProGuard, aleatory, and -o, they used string encryption. That's why their percentage is much less than in no obfuscation dataset. But if you're comparing, for example, all strings in ProGuard and all strings in no obfuscation, we have that on obfuscation dataset, our system performs better. Why we have such like this situation? It's actually very interesting because ProGuard obfuscation, they remove all the libraries which were not used in the application, and it's like we comparing the size of the tokens which were extracted. For example, no obfuscation, we extracted more than 1 million of features. On ProGuard, it was only several thousands. So it seems that the data like was on this APK like libraries, so it was more clean. That's why our system performed better after ProGuard obfuscation. So also very interesting moment that application strings in every dataset in ProGuard, aleatory, and -o show the same accuracy 62% because obfuscation which we were used, they don't apply on application strings. It's only apply on DEX strings, all strings like reference and unreferenced strings. So application strings, they're stable. So our contributions, we created a framework for generating profile of malware authors, and proposed system achieved 98% for attributing 1,559 benign Android applications, 96% for attributing malicious and 71% for attributing obfuscated. We also made analysis already existed system DINC. DINC system, they only capture Java source code. Like they develop these features which can be extracted from Java source code, like different type of the bracket, different type of the comments. So we applied this system to our APKs, and we receive only 50% of this system. So our framework, they outperform existing systems. Thank you so much for your attention. If you have any questions, please ask me. Yes, please. Yes. Okay, thank you so much. The question is like which machine learning technique we used in this framework. We used supervised learning because we had our data is labeled. Like we have labels authors of every APK. That's why we use supervised learning. We use the SVM. We didn't compare our results with different machine learning techniques. For example, no, we can implement neural network or random forest on it. It's our future work. About unsupervised learning, yes, like we can use clustering if we have unlabeled data. So if we have unlabeled data, we can make this clustering, and every cluster can actually identify the author. Yeah, but it's much more complex approach. In our research, we have labeled data. That's why we didn't touch unsupervised learning. Thank you. Any other questions? Thank you so much. Have a good rest of the day. Thank you.